Hello everyone, welcome to my class of electrical power system analysis. My name is Francisco Gonzalez-Longatt, and the topic today is power flow or steady-state analysis of power systems and voltage control. And I have included application, a couple of examples using DIgSILENT PowerFactory. Okay, before I start, I would like to say that this is a short class and is not intended to provide the full background about power flow analysis. Okay, there is a different video, a longer video talking about power flow analysis, all the basics. Okay, however, in this short video, I would like to introduce few concepts needed and also few explanations about details in order to make connection with DIgSILENT PowerFactory. Okay, some of you contact me and ask me the direction of my repositories. Here you can see the ResearchGate direction. Please feel free to go over there to ResearchGate and download the full slides. And also examples included in these slides can be downloaded from my personal GitHub. Okay. Also, I highly suggest, if you have time, please follow me on Twitter. You can see over there, and also if you can add me using LinkedIn, that is beautiful. Extremely happy to receive feedback. Okay. Well, let's go for the class today. What is the objective? Well, the idea today is to introduce the main concepts related with the AC power flow. Basically, today is the classical AC power flow using positive sequence, three-phase system, balanced systems. Okay, and then we will use DIgSILENT PowerFactory for calculating some power flow and show some features related with PowerFactory regarding voltage control. Okay, what is the agenda today? Well, we have a relative short agenda. I will start with a short introduction about power flow. What is power flow? Then I will go for the power flow as a circuit problem. I will try to make a connection between what is the load flow or power flow, and then with the theory that you know from circuit analysis. Then I will go for some theoretical background, nodal admittance matrix, an example about nodal admittance matrix, power balance equations. I will introduce the problem formulation of the load flow, some numerical methods used to solve the power flow, a short comparison of the different power flow solution techniques, few comments about network representation and calculation methods, and then two practical examples. Those examples are not designed to a full understanding of the load flow or power flow function inside PowerFactory. It's assumed that the student understand and know how to perform load flow. However, I will introduce a couple features. One of them is a command dedicated for comparison between simulations, static simulations, and then I will present something related with steady-state voltage control. Okay, the idea is make a connection with voltage dependence of loads and also some basic introduction of the effect of including distributed generation at distribution level. Okay, well, let's go for business. And as you must be aware, the idea of the power flow or load flow is to calculate voltages, current, active power and reactive power and power factor inside the power system. However, you must realize that the classical power flow, this is a static study, or what I mean is a steady state condition. When you are calculating the power flow, what you are getting is the steady state of the power system. You are using phasor for voltages and currents, and you are using impedance and admittance for the network model, okay? This is probably the most used computational procedure in power system analysis. What is the reason? Because planning, design, and operation of power system require a lot of many information regarding what is the steady state performance, okay? And also typically is the most used power system study, because it's also the input for some others. If you are running if you are calculating power system protection, you need to know what is the low current, what is the overload current, and typically we use a power flow analysis in order to get that right, okay? What is interesting is that we need to know, for instance, what is the nominal low current and what is the maximum low current, and typically we want to know what is the effect on the power system under different configurations. That can be done using the power system, the power flow, okay? There are many power system indicators for the power utilities that require assessment day by day, and many of them are coming from the steady state analysis. For instance, if you want to know what will happen in your system if one transmission lines is put out the service, you can run the load flow and see what are the voltages and currents, and see if there is any device that is overloaded, okay? What I want to say is that the power flow is probably the most used power system analysis study, okay? Okay. Now, what is the problem about power flow, okay? Well, the power flow formulation is very simple, okay? It's like the circuit analysis. In any circuit analysis, you have some variables that you know the value of them, and there are some unknown variable or variables that you want to know. For instance, if you know the power consumption and all the buses, that's mean P and Q, active and reactive power, and also you know the system configuration, I mean you know all the impedances and admittance and so on, and you know what is the power production in some generators, then you can calculate what is the power flow moving through each transmission line and transformer. And also you can calculate the voltage magnitude and phase at each bus bar. The idea of power flow formulation is extremely simple. You have some variables that you know, P, Q, some impedance, admittance, and then there are some variables that you unknown and you want to know. Now the connection is that you need to solve the network. You need to use some mathematical rules in order to get those unknown values, okay? And what is the best example that I can give you in order that you understand the power flow formulation? Okay, you are top expert in circuit analysis. You took many trainings and many courses related with circuit theory, and you must remember this kind of exercise. You know the resistance R1, R2, R3. You know also what is the current moving in this series connection, and somebody is asking you what is the terminal voltage that allow that current going through the circuit. Well, what you are doing is you have some known variables, and there is the terminal voltage, one variable that is unknown. What you need to do is simply it's simple. What you need to do is apply some mathematical rule coming from physics that define the relationship between voltage and currents. from circuit analysis, you will remember that is Ohm's law. Ohm's law can be used in order that if you know the resistance, if you know the current, you can forecast or you can calculate what is the voltage. In this case, the total resistance, 225 ohms. Here, the current that is moving, that is going through the circuit, 0.5 amps. And then using Ohm's law, you get the value of the unknown variable, in this case, terminal voltage, and the numerical value, 112.5 volts. What I'm trying to say is every time that you are solving a circuit, what you are trying to do is get the unknown variables, okay? In this case, it's extremely simple, it's extremely easy, because the unknown variables are voltage and currents. And to be honest, classical circuit analysis is based in linear system. As this is a linear system, the equation that is defining the physics, Ohm's law, is a linear relationship, and you are using algebraic variables. To be honest, circuit analysis in this sense is extremely simple. But now let's go to the power flow formulation. Power flow formulation is a bit more complicated, however, is similar to what we discussed before. In circuit analysis, we have voltages and currents, and we have one parameter that is the resistance. But in power flow, well, for each bus bar, you can see over there a table, and there are some knowns and unknown variables. You can see the question mark that is present in red color in this kind of table. And you can see in some bus bars, there are loads, and you know the active and reactive power. But in those loads, for instance, the bus bar number 1, you know the value of this active and reactive power, but you don't know the voltage. As a consequence, that is one unknown variable. Now, probably you will resemble, this is similar to circuit analysis. You need to get some physics in order to find the relationship between power and voltage. And that is the reason that we call this power flow or load flow, okay? We know this power or load flow because the variables, the relationship is, the physics is between power and voltage, okay? However, I must be honest, in this case the problem is a bit more complicated compared with the classical circuit analysis. One of the first reasons is, well, we are using complex variables. You must remember P and Q, they are the real and imaginary component of the complex power S, and also you are using phasors to represent the voltages. That means they are magnitude and angle if you are using polar representation. In summary, you are using complex variable. That is one of the complexity of the power flow problem. But the second one is a bit more difficult, and it's coming from the rule that is defining the relationship between voltages and power. Voltages and power, they are non-linear relationship. There is no linear relationship. I will explain that in few minutes, in few slides, but this is a non-linear problem. As a consequence, the main difference between the circuit analysis and the power flow analysis or load flow analysis is that here the relationship, the rule between voltages and power is a non-linear relationship. Okay? Okay, before I start this section about theoretical background of power flow calculations, I would like to say that this is just a very short, a very brief introduction about power flow calculations, okay? The idea here is just to introduce the basic concepts in order that I can use them for some practical applications later in this class, okay? If you want to go and have a full detail on power flow analysis, I highly suggest that you go to my YouTube channel. There is a specific video regarding this topic, and you can see the full explanation about the power flow analysis, okay? It's very important that you understand that power systems are similar. There are some similarities with circuit analysis. Of course, they are voltages and currents. However, the power system is a bit more complex compared with the classical circuit analysis. In real power system, we have complexities related with the performance of the devices. For instance, we have non-linearities coming from magnetic circuits of transformers and generators, and we have a lot of complexity coming from the behavior of different electrical machines and loads. Okay. However, another big difference between power system analysis and circuit analysis is the size of the problem. It's not typical that you find a very large circuit during your circuit analysis classes. Okay, power system, on the other hand, they are designed to be big. It's not rare that if you are working in a transmission system operator, you will be dealing with very big, very large power system, 1,000 nodes, 1,000 branches. Okay, what is the reason for this introduction? Because basically the matrices and vectors are quite useful if you are dealing with big power systems. Okay. If you remember, Ohm's law defined the relationship between voltage and currents, and you can write Ohm's law in a matrix and vector expression. Here we have the bus voltage equal to the bus impedance multiplied by the bus currents. Okay, when I say bus voltage, this is a vector, and the components inside this vector represent the voltages in each bus bar. Okay. Also, we can use admittance matrix. Admittance matrix again is a matrix, is a square matrix, and this matrix represents the model, the steady-state behavior of the power system. Why? Because we are using first the linear relationship between voltage and current. Second, we are using complex numbers, and we are using phasors to represent voltage and currents. Okay. To be honest, the admittance matrix is coming from the Kirchhoff current law, and it's extremely simple to see. Okay. The next step that I will do here is I would like to introduce just a very brief explanation about the mathematics behind the nodal admittance matrix. Okay. If you imagine any series device, a branch, there is an admittance or impedance representing this device, okay? And this device is connected between two different bus bars, bus bar I and bus bar J, where the terminal voltage, they are known, okay? Now you must remember from various circuit analysis, we can define the current moving through this branch, series branch, like the voltage difference between the terminals, and divide by the impedance. You can use admittance and the relationship will look much better, okay? But this is the equation for a single device. What's happened if we have a very big bus bar, and this is the bus bar K, and they are end elements connected to this bus bar, including one element that is going to ground. Okay, well, again, we can use this equation here for calculating the current through the impedance, and also we can include here the equation for the component or the device that is connected to reference. Reference voltage equals 0. You can see here, extremely simple the equation. Okay. But inside the power system, we got the equation for the bus bar K, but in a power system, this bus bar K have n currents, and we can define the current going in like the sum of all the currents going out. Well, we can write here the Kirchhoff current law, very simple. We can put together the expression of the current at the bus bar 0, 1, blah, blah, blah. We put together inside, and we got this beautiful linear relationship here. This linear relationship say that the current that is going inside the bus bar K is equal to the sum of all the currents going out. In other words, this is just a very basic application about Kirchhoff's current law. Okay? However, now if we assume that we have n bus bar inside this power system, now we have the current for the bus bar 1, bus bar 2, bus bar 3, bus bar n. Something that you must realize, this is a linear system because the relationship between current and voltages is defined by the admittance, and this is a set of linear equations. Of course, we are using algebraic variables. Those are complex numbers. Voltages represented by phasors, current represented by phasors, okay? Now we can use very basic mathematics and move from n linear equations using matrices, and voila, we have here a n by n square matrix, and this receives the name the bus admittance matrix or the admittance bus matrix, and here you have a vector that represents the voltages at each bus bar, and this is the current that represents the components, currents going inside each bus bar, okay? Now, you can see it's extremely simple. We have the admittance matrix here, vector for voltages, vector for currents, and we can identify what is the expression for each element inside the admittance matrix. The admittance matrix have very beautiful properties I will discuss in a minute, but I want that you understand that the diagonal here, the diagonal section of this matrix, it's what we call self-admittance. The self-admittance is defined like the sum of all the admittance connected to the bus bar. It's a very basic concept. But there is one that is defined the mutual admittance, and the mutual admittance depends on the terminal of the bus bar, and is the negative value of the admittance connecting those elements, okay? Okay. Now let me tell you something. The admittance matrix is extremely important. One of the reasons is because this represents the topology, the way that the system is connected, but at the same time involve all the electrical parameters, I mean the admittance of every single component, okay? However, you must understand something. The admittance matrix is a matrix. Is something that is abstract. It's not necessarily a description of the physical connection inside the power system. What I'm trying to say is the admittance matrix includes the connection, the topology inside, but using the admittance matrix, you cannot go back and find the topology, okay? Interesting property of this matrix is a symmetric matrix. As you can see here, the elements above the diagonal and the elements below the diagonal, they are mirror each other. As a consequence, that is the basic definition for a symmetric matrix, okay? Another interesting thing here is, in this case, the matrix is very sparse. What does it mean? In this case, the admittance matrix have many elements that they are zero. To be honest, it's very, very typical that the admittance matrix has many zero elements. To be honest, the admittance matrix is very heavy in the diagonal, but outside the diagonal, you will find very small number of non-zero elements that create sparsity, okay? For instance, in a system with 1,000 nodes, if each node is directly connected with 3 branches on average, we are talking about that this matrix that's supposed to be 1,000 by 1,000, it will have only 4,000 non-zero elements. That means that this matrix has at least 0.4% of the elements that they are non-zero. That means 99.6% of the matrix is filled with zeros.